Kutschera, director of the Vera Laboratory, Vienna Environment Research Accelerator, and head of the Institute of Isotope Research and Nuclear Physics of the University of Vienna. He is a leader in the field of Accelerator Mass Spectrometry. He did a lot of work. He has many research interests in nuclear physics and Accelerator Mass Spectrometry. I just summarize his curriculum. In 1965, he got his PhD in experimental physics at the University of Graz in Austria. And he was for 3 years first a visiting scientist and then assistant professor at the Untitled Accelerator Lab at the Max Planck Institute of Nuclear Physics in Heidelberg in Germany. Then he moved and he was a research fellow in Japan at the University of Tokyo. First for 7 years and then 6 years he was a visiting scientist at the physics division at Argonne National Laboratory at the Department of Physics at the Illinois States. And then Berman, visiting professor at the Raka Institute of Physics at the Hebrew University in Jerusalem, visiting professor at the University of Radium, Institute of Radium Research and Nuclear Physics at the University of Vienna. Since 1993, he's professor at the University of Vienna and head of the Institute of Isotope Research. The title of the seminar is Accelerator Mass Spectrometry and Many Facets of C14. Walter, the microphone is yours.
Thank you very much. I'm really happy to be here in this part of Italy for the first time. In fact, I never went that far south in Italy before. What I would like to do today to tell you in essence how much fun we can have to use carbon-14, not only for archaeology, which is well known that carbon-14 is an important isotope for dating in archaeology, but in many other fields. And in fact, I think this field has no limit I can see at this point. Any new laboratory starting measuring carbon-14 will have enough to do for many years to go. And I'm happy to see that in this region there's also a facility now, which I had visited briefly yesterday. The title says the many facets of carbon-14 application. And I was lucky 10 years ago when I moved back from America to Vienna to start a facility there, an AMS facility, which does much more than carbon-14 by now. And perhaps someday you will also extend your facility to different isotopes. Because EMS is such a wonderful method to study isotopes of any element. This is the big power. I think it is not said too much to say that it is perhaps the most versatile instrument to use isotope signatures to study our environment in every section you can think of. Atmosphere, biosphere, hydrosphere, cryosphere, the big ice sheets, the lithosphere, the solid part of our Earth, and also the cosmosphere, that is all the cosmic material arriving at the Earth. And finally, what we call sometimes technosphere, that is all the changes or effect of humans on nature, we can study by using this method. Now, everything starts, of course, with history. And the most important input of nature for our field are cosmic rays. Cosmic rays, of course, we know now they impinge on the Earth, on the surface of our atmosphere, and produce nuclear reactions in the atmosphere, like they hit the nucleus in the atmosphere and produce a lot of secondary particles. The historical part I'd like just to mention very briefly is that cosmic rays, or cosmic radiation rather, was discovered early last century. And as it happens, it was discovered in the institute I'm working now. Okay, maybe you can see it. Yeah. This is a picture of Victor Hess in 1912 when he took balloon flights up to 5,000 meters to study the ionization of air. At that time, nothing was known about cosmic rays. The only thing you could do is study how air is ionized as you go up. Of course, you had to take a confined volume of air with you. And this was a tremendous achievement at that time to do a measurement in a balloon. This is actually Victor Hess showing him in 1912. And he was awarded the Nobel Prize for that many years later, for his discovery that the ionization increases. The ionization in the air increases by a factor of 3 when you go up to 5,000 meters. 1,000, 2,000, 3,000 meters, nothing much happened. Only when he reached this great height, which at that time was very difficult to do. Anyway, many years later he received the Nobel Prize in Physics, together with Carl David Anderson, who discovered the positron just a few years before that time. Also as an effect of cosmic rays, of course. The second person who is very important in this connection, of course, when I talk about carbon-14, is Willard Libby. Willard Libby at the University of Chicago in the late 40s, after the Second World War, developed his method of using carbon-14. Now, by now, this is so well known that it's difficult to really acknowledge the achievement of the thinking of Libby at the time to figure out that this is actually possible to use it. All we know now, of course, there's a radioactive decay law, and carbon-14 decays from some initial value with an exponential decay, and as a function of time, the half-life is known. As a function of time, this initial carbon-14 content decreases. So after one half-life, it's 1/2 and so forth. And right now, with our present techniques, both with accelerators and decay counting, we can go back 10 half-lives, roughly. So we can measure carbon-14 when it's reduced by a factor of 1,000. The wrong assumption at the time was that carbon-14 was stable, or is stable in nature over all times. But the big achievement, I feel, was that Libby figured out what's going on in the atmosphere. And this shows you a scheme, what we know now. And 50 years ago, Libby got it right, almost completely. And this, I feel, is his big achievement, that he believed that this actually happens in the atmosphere. So, primary cosmic rays produce secondary neutrons. They are captured in nitrogen-14 to produce carbon-14. So these are nuclear reactions. After that, chemistry sets in the atmosphere. The carbon-14 atom is quickly oxidized to monoxide, carbon monoxide. And then, with a different reaction, and this is known very well now, it's mainly reaction with the hydroxyl radical, which is extremely low in abundance in the atmosphere. It's further converted to CO2. And then it enters the different archives or different domains on the Earth. And as a result of all this, we have a distribution of isotopes like this in carbon, which is within this exchange, which has the two stable isotopes and very little carbon-14. You see 10 to minus 12. And most of the carbon-14 is actually stored in the oceans. Only 2% is in the atmosphere, 93% in the ocean, and about 5% in the biosphere. And this is a big dynamic system. There's exchange going on all the time. About 1/5 of the total CO2 in the atmosphere exchanges per year, goes through into the biosphere, the ocean, and comes back again. So there's an enormous dynamic going on all the time. And as a result of this, carbon is distributed, and this was the big idea of Willard Libby, that this actually must happen without any proof first. It was really a thought experiment, and finally he found carbon-14 in nature as a natural carbon-14. Now, the only thing we have to realize here is that first it was extremely hard actually to measure. Maybe this can be focused a little. Yeah. If you go through a quick calculation of 1 milligram of carbon, a typical material, 1/1000th of a gram we use in an accelerator now, how many atoms you have in that, assuming this isotope ratio, you still have 60 million carbon-14 atoms. Now, the decay of these 60 million atoms lead only to about 1 carbon-14 decay per hour. If you do the same measurement with isotope ratios in an accelerator, you can count about 500,000 atoms in an hour, and this big factor gave this enormous boost to using carbon-14. But Libby, who had only this method available of counting the beta rays, figured out everything by very elaborate experiments using many grams of carbon and getting a very weak signal, but still having the right idea. So we certainly owe him this great method, there's no question, and he was rightfully rewarded with the Nobel Prize in chemistry for that, interesting in chemistry, not in physics. Now, what I want to do, and I'm sure I will run out of time eventually, but I will tell you, give you examples of use of carbon-14 in the atmosphere, then discuss a little bit about application of the hydrosphere, and then in the biosphere, namely some archaeological applications. The first thing we got involved in Vienna was a collaboration with one of the Max Planck Institutes in Germany, chemistry in Mainz, to study this process. That is to measure actually carbon-14 monoxide in air samples. And this involves very interesting chemistry, which is of great interest to today to understand what is going on with trace elements. Here is the production of carbon-14 monoxide by this nuclear reaction and the first step in the chemical reaction. The OH radical, which is important for converting the monoxide to dioxide, is produced in a process which involves ozone, light, and water. In the first step, you break up ozone into a regular molecule and an excited atomic oxygen, and that reacts with hydrogen to make the radical. Now, these are all variables. Light is a variable over time, of course, the seasons and day and night. Ozone is also a variable quantity, and water vapor in particular is a variable. So the production of OH is changing very rapidly, even within a day, within hours. And it is so reactive that it only lives 1 second in the atmosphere before it reacts. So it is not very difficult to monitor it directly. And the basic idea is that carbon monoxide can be used as a monitor because the carbon-14 monoxide concentration in the atmosphere is a function of how much OH is available. If there is more OH, the concentration goes down. If there is less OH, it stays at a higher level. So the carbon monoxide concentration of carbon-14, it is a constant production on a short time scale of this carbon-14 monoxide, but the equilibrium concentration depends on how much OH is there. This is the basic idea why this could be useful. to study. And so we had an experiment performed in collaboration with a number of institutions, especially this Max Planck Institute for Chemistry in Mainz. And we took samples from a high altitude observatory in the Austrian Alps, similar to the, say, the Jungfraujoch in Switzerland or the Zugspitze. Now, I cannot describe any of the detail of the measurements. Just to tell you, if any of you likes mountains, this is a beautiful way to do experiments. Of course, this doesn't show very well here. Anyway, this is a mountain, so I think I can skip all these figures which show the mountain. So I just show you the results of what comes out from such a measurement. What this shows is about 2 years span of measurements. This is the concentration of carbon-14 molecules per cubic centimeter air. So you see, it's very small, only 20 molecules. A cubic centimeter of air has about 10 to the 19 molecules. So it's an extremely small concentration. But anyway, I can't describe how this is done, but it can be done. Believe me that all this scattering you see here is real. Has nothing to do with measurement technique. It's real scattering of data. So what you see roughly is that in January or in winter time, you have a maximum, and in summertime, in July, it goes down, and then it goes up again. And of course, there's some scattering. Well, the difference between summer and winter is easy to understand. In summertime, there's more light. There's more water vapor also in the atmosphere, so there's more production of OH, and the CO goes down. In wintertime, it's the reverse. Now, the interesting thing is this group. You see, this is in wintertime, and we got data which essentially are similar to summertime values. And to understand this, we ask meteorologists to calculate where the air which we measure, take in on top of the mountain, actually is coming from. Because you know, the troposphere is a dynamic thing. The air doesn't stay there for many days. So, and this can be done very well these days. You can calculate where the air is coming from, where it was 4 days earlier. And this shows where it came from. Maybe you can see. Right now we are here, as you know. And it looks that the air, which actually ended up here, where we measured it, started from a latitude very close to Lecce, but in Spain actually. So it traveled this way. This can be done with very well now in meteorology. And you know, the weather is predicted pretty well these days. And this is because one can do such a good job in predicting, first predicting, but also going back in time. Of course, this is easier to go back in time and say that 4 days earlier, the air which we measured here was actually in south of Spain with more light, so it represented the summer value rather than we measured it we took the sample in winter, but the air actually had a signature from summertime. Okay, so this is a short story on this my first subject. The second one, I want to tell something about our big reservoir of carbon-14 and the big reservoir of water, of course, the oceans. And this is a work which was not done in our laboratory. In fact, there's a whole facility set up to study this. But the basic idea is the following: that what you see here is is our Earth, and these here are the oceans. And what is shown here, these numbers, is the apparent age difference you measure when you take a water sample from the surface and from 3 kilometers deep in the ocean. And you measure the carbon-14 content. And that gives you an age difference, because the surface water essentially is in exchange with the atmosphere. So it represents more or less the atmospheric value. And if the water is disconnected from from the surface, then carbon-14 decays, just like in an archaeological sample. So what you see here are these numbers, age differences in years. You see the North Atlantic here has relatively small numbers, 100. If you go south, this number increases, 500 in the South Atlantic. If you go to India, it increases further. And if you continue here into the Pacific, it's close to 2,000 years. What that means is that between the surface water and the deep water is a much smaller time difference in the North Atlantic as compared to the Pacific and the Indian Ocean. And from that, a beautiful model was conceived by Wally Brooker from Columbia University. You probably have seen this perhaps before. This is very simplified. It's again the same thing as Libby. It's not true, but it explains a lot. Not true in detail, but the general idea is that warm surface water from the equatorial region is moving towards the North Atlantic, and by some process it then goes deep in the deep sea and returns here. And for continuity, it has to be a closed loop. So this is why it's called conveyor belt model. And now we understand, this was the result of the measurements I showed. We understand that the age difference between surface water here and deep water here must be small compared to here, when it has traveled around the world in the deep sea, disconnected from the surface, and so it aged. The water becomes older and older, whereas the surface water has always the same. It's the reference age. It's always the same. So this is a beautiful model, and it's a sort of zero order description of a big movement of water and heat from the equatorial region to the northern latitude, and this is extremely important to understand our Earth as a whole. Now, the first set of data which I showed were done with classical carbon-14 counting, beta counting. Big water samples had to be taken, like I think it's shown here, something like 250 liter for beta counting. Now we need only half a liter of water when we do an AMS measurement. And the oceanographic community in the US has set up a facility 10 years ago and has measured by now 14,000 water samples. This is an incredible work. I cannot recommend it to anybody. It's very interesting for oceanographers to make models, and then this shows a map of this so-called World Ocean Circulation Experiment. All the blue dots are measuring points. I mean, these were big cruises of ships, and then they took a profile going down in the deep sea, and Carl von Reden, who is at the Woods Hole Oceanographic AMS facility, he showed this figure in last AMS conference in Japan, and he mentioned that there will be a follow-up program. All these red points will be measured in the next few years, so new samples will be taken. Because not only is it important to take a snapshot of the ocean, you have to see what is going on in 10 years. So every 10 or 15 years, a new survey has to be made. Only then we can hope to understand some of the dynamics we want to learn, namely how much CO2 of our additional CO2 ends up in the ocean. This is the big interesting quantity we want to know. Now, from the so-called WOES project, what came out of it? I just show you one example. I have no time really to do more. What this shows are cross-sections at two different depths through the Pacific. All these white dots are actually measuring points. And this measures the carbon-14 content. And deep blue means it's old. Yeah? It's old carbon-14, so it's old water. And red means it's more recent. And for instance, well, you see that clearly the northern Pacific has older water than the southern Pacific. But what's interesting is here, you see a dynamics you can only find out with such measurements, that near the bottom, at 4,000 meter depth, young water is apparently penetrating to the north, which you cannot see here at this level. So there is, not only is there big dynamic on the surface going on, but even as a function of depth, there are different movements. And all of this we have to understand if we want to make a reliable global model of what is going on our Earth in terms of big transport of water and heat. Now, I'd like to mention just a different isotope in this connection, which became of recent interest. As you all know, nuclear power produces radioactivity, and in Europe there are two big reprocessing plants, namely in France, La Hague, and in England, Sellafield, which reprocess all the spent fuel rods, and they release certain isotopes into the ocean. And one of them, which can be measured very well with AMS, is iodine-129. And a total of about a ton of this isotope has been released here in the ocean, and is now moving first on the surface, and later it becomes part of this conveyor belt which I mentioned. And since we know exactly how much we put in, we can follow it and check whether this whole model are really true. And I show you, and there are also other isotopes like technetium and uranium-236. All of them are produced in nuclear power plants. And they can be measured now very sensitively with AMS and can be used to check this concept of the global distribution of water. This is what I always call, of course, they were not put in for that purpose. they were put in as a garbage from the processing. But as it turns out, it becomes a very useful isotope. It's also produced naturally, but at a much lower level. So it's a very strong signal which we put into the ocean, and it can now be followed. And especially French and Canadian collaboration started to use this. And what I show you is a measuring point here in Iceland. At the here's about 3,000 meters, and this ridge, here's the island of Iceland, and in between is about 1,000 meter deep. So the water, actually, when it flows to the south, it has to go over this, like in a bath tube. And I show you just one example. French show everything different. I mean, we show going from top to bottom, like here, but they show it this way. But we know the French are different, and eventually we understand what they're doing. So here is the surface of the ocean, and here it goes into the ocean. And as you see, the isotope ratio is very small at the surface and all the way down to 1,000 meters. That, yeah, not easy to see. This is a figure which shows the Earth's magnetic field and the solar magnetic field, and cosmic rays impinging on the Earth. On the surface of the Earth, they have to penetrate all these magnetic fields, and they are affected by that. We know this quite well now, and this is part of the variation of the carbon-14 production because the magnetic field is not constant. Now, as a result of this, those who do carbon-14 know that carbon-14 is not stable as a function of time. We go here from our time back 15,000 years. BP means before present. And this is what Libby assumed, that carbon-14 is constant all the time. And if you actually measure the carbon-14 as a function of time from 3 rings, which you can date absolutely, you get these deviations from a constant value. And you can see this is an extremely varying curve. There's large changes, but there are also small fluctuations. And all of this has an effect eventually for the carbon-14 dating, because we have to know what the carbon-14 content was at a particular point in order to figure out time. Now, these fluctuations, which you see here, have to do with changes in magnetic field, mainly, but could also have to do something with the exchange of the different reservoirs, like the ocean inhales some of the old carbon-14 into the atmosphere. But all of those variations, we believe, are natural, have nothing to do with man. But in very recent time, we have also an effect of man on the carbon-14. As you well know, that these are the last 50 years. Again, this is the deviation of carbon-14 from that reference value, this natural level. That in the 50s and 60s there was a big increase of carbon-14. These are measurements of carbon-14 in CO2 in the atmosphere. And this peak was produced by the nuclear testing in the atmosphere, because they supply neutrons, the bombs, and they convert nitrogen-14 into carbon-14 just like neutrons from cosmic rays. And it was increased by a factor of 2. And then in 1963, now this the next figure I think we cannot see, but maybe a little bit. In 1963, yeah, maybe the older people here know that this is John F. Kennedy when he signed the nuclear test ban, atmospheric nuclear test ban treaty in 1963. 6 weeks before he was assassinated, this picture was taken in the Oval Office. This is Johnson and other famous figures. I just happened to came across this picture when I once serving on the internet came into the Washington Library, and I found this picture. They asked him to send me the picture, and they did right away. So here was the point where it was stopped, and then carbon-14 distributed to different reservoirs. And what is important for the whole carbon-14 method is to see that the difference between southern and northern hemisphere